Welcome back to The Explainer. Today, we're diving straight into organometallic highlight perovskites. You already know these materials are completely reshaping renewable energy, right? But to understand what actually makes them so incredibly powerful and what's creating quirky behaviors like anomalous hysteresis, we've got to look closer, like zooming into the atomic level closer.
Because that brings us to our core microscopic mystery. What exactly happens inside a solar cell at the exact fraction of a second a photon hits it? Obviously, we know light creates electricity, but the dynamic physical reaction of the material itself? Well, that's a wildly complex process that scientists are really just now fully mapping out. Okay, let's dive into this. Here's our roadmap for today. We'll start with the next generation solar cell, unpack the photo-induced Stark effect, look at the role of dipoles, contrast red versus blue light, map out moving ions with light, and finally, wrap up with building better panels.
Right. Section 1. The next generation solar cell, a macro-level revolution. So when you look at this complex crystal structure of the methylammonium lead iodide perovskite, try not to see it as just a rigid lattice. Instead, visualize it as a crowded, microscopic dance floor. You've got lead and iodine forming these cage-like octahedrons, and tucked right in the center are those organic molecules. Right now, they're just hanging out, waiting for the light to hit. Basically waiting for the music to start. Which brings us to Section 2, the photo-induced Stark effect, or when the music starts. Now, when that light finally hits, the material exhibits some quirks like anomalous hysteresis and a noticeably slow response. To understand why, we have to look at the Stark effect. This is essentially a shift in optical absorption caused by changes in the local electric field within a material. To put it simply, when light enters our perovskite dance floor, it doesn't just knock electrons loose. It actually alters the entire internal electrical environment. The material's ability to absorb light shifts because that local electric field has been messed with. And this brilliantly illustrates exactly what's happening. On the left side, notice the perovskite structure reacting, with those arrows indicating the local field changes. Then over on the right, in the band structure diagram, the red and blue arrows show the excitation of electrons. But look closely at how the black curves of the bands themselves are shifting. The light has induced an internal electric field that perturbs the entire system right at the band edge. So, literally, the dance floor is warping right under their feet.
Let's move to Section 3, the role of dipoles. Meet the dancers.
To really grasp this warping effect, researchers tested the dancers themselves by swapping out the cations sitting inside those molecular cages. Think of these dipole moments as kind of like character stats in our microscopic dance. We've got methylammonium, or Ma, coming in with a strong dipole moment of 2.22 dBi. Then formidinium, Fa, with a much weaker 0.19 dBi. And finally, cesium, an inorganic atom with a dipole of exactly 0. Well, the researchers found something amazing here. A stronger dipole acts like a shield. Ma has a massive shielding effect against sudden electric field changes, but cesium with its 0 dipole, low shielding, which results in the absolute strongest Stark effect. So the type of dancer directly dictates just how violently the dance floor shakes. Moving into Section 4, red versus blue light, changing the tune. So we know the dancers matter, absolutely, but what about the music itself? The researchers decided to set up an A/B test. Red light at 630 nanometers is lower energy. It provides just the bare minimum thermalization energy to cause a stark shift. It basically just makes the atoms sway gently to the music. But blue light at 470 nanometers is super high energy. It pumps massive excess thermalization energy right into the crystal. It's not a gentle sway anymore. It's a high-energy mosh pit that causes sustained, lingering physical changes in the material. Now, what's really interesting about this slide is the voltage decay graph in the bottom left, which was recorded in the dark after the light was turned off. See those red circles? That shows what happens after red light illumination. The voltage drops relatively quickly. But look at the blue circles. After blue light illumination, the voltage decay is vastly slower, dragging out over many seconds. Now, why would the cell hold on to that voltage for so much longer just because the light was blue? Well, this lingering effect hints at something profound. The high-energy blue light didn't just move electrons, it physically moved entire atoms within the lattice. Section 5, moving ions with lights, the atomic choreography. This is wild. The excess energy from that blue light actually forces ions to switch places on our microscopic dance floor. So this isn't just an electronic reaction we're looking at, it's a structural one. researchers managed to translate these ridiculously dense quantum calculations into an elegant, easy-to-follow chemical cascade. Step 1. The light hits, causing a charge transfer that changes bond lengths and physically tilts those lead-iodine octahedrons. Step 2. Because the cage tilted, the delicate hydrogen bonds between the trapped organic cation and the surrounding halides shift. And step 3, the organic cation rotates in response, and an iodide ion is physically displaced from its position in the lattice. It actually moves. Let's move to the visual and see how this builds. Check out this schematic. On the left side, the green arrows show the tilting and bond shifts we were just talking about. Now on the right, focus on that red arrow swooping around the molecule. That is the actual ion movement. The excess thermal energy from the blue light excitation provides enough localized heat to overcome the activation barrier, which allows that iodide ion to jump to a completely new position. Guys, the light is literally rearranging the architecture of the solar cell in real time. Finally, Section 6, Building Better Panels, from Micro to Macro. To pull back from the quantum realm and connect this choreography to the real world, consider this number. The state-of-the-art mixed perovskite device in this study achieved a 19.2% power conversion efficiency on a backward scan. So the crucial point is that this isn't just some abstract theoretical chemistry. Remember those quirks we mentioned at the start? Hysteresis, where the efficiency actually changes depending on how you measure it, is deeply tied to this very ion movement we just mapped out. By understanding how the dipole of the cation shields against the Stark effect and exactly how different light wavelengths trigger ion migration, engineers can design new chemical mixtures to lock those atoms in place and stabilize that impressive 19.2% efficiency across the board. Which leaves us with this huge question. How will mastering this atomic dance ultimately power our clean energy future? Think about it. We are no longer just catching sunlight. We are engineering the exact way atoms vibrate, tilt, and shield themselves at the quantum level to create the ultimate solar panel. It's a massive testament to how solving the smallest possible mysteries unlocks the biggest solutions for our future. Thanks for joining me on this explainer today, and as always, keep asking the big questions.